My name's Sian, and my PhD project looks into understanding the mechanistic pathway of alpha-synuclein aggregation, which is associated with Parkinson's disease. So Parkinson's disease is a neurodegenerative disease which has become more prevalent due to the increase in human lifetime expectancy. It is currently one of the most prevalent neurodegenerative diseases of our time, with over 7 million people suffering from the condition worldwide. So alpha-synuclein is the main protein associated with Parkinson's disease. It is a protein which exists naturally in the brain in a disordered structure. However, under certain circumstances, it is able to aggregate to form amyloid fibrils, which are made up predominantly of beta sheet structures. It is these aggregates which are associated with Parkinson's disease. So alpha-synuclein usually exists in its monomeric form, but as I said, it is able to aggregate. And when it does, it will initially form oligomeric species, which are smaller aggregated structures like dimers or larger. Then these aggregates can form protofibrils, which can then go on to form the final fibrillar species, which are the hallmark of Parkinson's disease. What's really interesting though is that in recent years, it has been these smaller oligomeric aggregates which have been identified as a toxic species associated with Parkinson's disease. They are thought to disrupt the cell membrane and eventually cause cell death. Currently, the main technique used to monitor the aggregation of synuclein in vitro is through the use of THT intensity assays. THT, or thioflavin T, is a fluorescence molecule which, when free, has a low fluorescence intensity. But when bound to beta sheet fibrils, it has a much higher fluorescence intensity. This enables synuclein aggregation to be monitored from the fluorescence intensity of THT and usually shows a very characteristic sigmoidal curve. An example of this type of plot is shown now. However, this type of plot can be limited as it reports mainly on the presence of fibrils and gives very little indication of when oligomers and early stage aggregates begin to form. And this is really what my project is all about, determining a way to detect these species and further characterize them. One way of doing this is through the use of molecular rotors. Molecular rotors are fluorescent molecules which can give an indication of the viscosity of their environment based on their fluorescence lifetime. Molecular rotors like THT, which I've mentioned before, and DIS2, both have an intramolecular bond about which free rotation can occur. In very low viscosity environments, the molecule is free to rotate about this bond, and so when excited, it can relax back down to ground state via non-radiative decay pathways, like internal vibration, and therefore it has a very short fluorescence lifetime. In contrast, in higher viscosity environments, like the environment created by fibrillar species, this rotation is now restricted, and so upon excitation, the radiative decay pathways now dominate, and so the molecule will have a much longer fluorescence lifetime. During an aggregation of alpha-synuclein, we would expect the viscosity to increase as smaller aggregates and then larger fibrillar species begin to form. This variation in viscosity can therefore be detected and monitored by these molecular rotors, and therefore could give insight into the structural pathway and mechanism behind the aggregation of synuclein. So really, the hope, as I said, is to gain an understanding of the pathway of aggregation of synuclein and take this further to begin to identify these toxic oligomeric species, and ultimately develop effective early-stage diagnostic and therapeutic techniques for Parkinson's disease. Thank you all for watching, and I'd like to thank all my groups and the CDT program for their support.